Okay, so now we'll look at the last question, question 6. So it just says this is just a search problem and a boat go from the bottom left to top right. It has 4 directions and like several actions, and each action has cost 1. So it can carry at most seafood pellet at a time. And if it goes to the go, then all the pellet will automatically be dropped off. First question, it asks us to calculate the size of minimum state space for this task. So first, needless to say, we should have M, N. This will represent the location of the boat. And next, we want to encode the food, like the food pellets here. So one easier way, like uses minimum space, is we have a list. And in the list, we have the food 1, food 2, food 3, and da. So they are the places that we encode the food here. And we can also represent whether the food 1 has 3 states. One is carried by the boat. One is stay, and one is already in the go, like already in the go position. So the boat has already carried it to the go position. So we can see we have K different pallet, and each pallet has 3 actions. So 3 states. So we can encode it as 3 to the power of K. And we also, after this, we also model the direction of the boat, which has 4 directions. So this will be our model for the minimum state space. For question B, mark all the answers that are true. First one, BFS will always find an optimal solution to the go. To solve these problems is not just memorization. If from memorize, we know that BFS or DFS, they're uninformed search, and also they cannot always find the optimal solution. But here, what is very important is each action has cost 1. So this means in the BFS tree, just like this, then one depth of the tree will only have cost 1, and here it have cost 2. So what BFS do is it will just look at this nodes and this nodes. So the early it finds like the go state, actually that go state will be optimum because it will cause the minimum cost. So for the first question, it's yes. And second, BFS will always return the same result as iterative deepening search. Iterative deepening search is actually pretty useful in reality. What it says is it will combine both DS is combine the space efficiency with space advantage of depth first search and the time advantage of BFS, breadth first search. What it do is, okay, so if this is the tree, the search graph, then in the first step, it will see, so if we only run depth first search, then it will go just along this branch. Maybe it will not end if it's see a loop, but here we just make sure first you need to, we limit the DFS with a depth limit of 1. So it will just search this node. And second, we limit depth first search with depth limit 2. And so it will search these branches, this node. So it is actually another case for another better version for BFS. So it also should be correct. C, when conducting UCS, the first path to the goal is, which is added to the frontier, will always be optimal. Yeah, for this question, it's also yes, because the UCS will find the goal according to their cost. And so for all the cost is 1. So it will also run as a BFS. So it'll also be correct. So the next question, it adds another agent, which is a pirate. So for a pirate, they will follow a fixed action sequence, and they always take the action to move forward if possible. And then they would also, they have 4 directions. So let S be the state space size from part A. What is the minimum state space size for the new problem? So we have S, and in this case, we have like for each pirate, they can be in MN state, MN space, MN location, and they also have 4 actions, and we have actually E pirate. So this will be our new state space. But another case is if you think the pirates are indistinguishable, you can also write this. This will also be a correct answer. S times 4m untruths E. Okay. Next question. Consider 3 heuristics for the original problem formulation. H1 is admissible, H2 is consistent, H3 is neither, but result in an optimal solution. And select all the following statements which are true. First one, H1 is still admissible for the new problem. So what we can notice is after we add the pirate, it will only like harm the situation for the boat, because when a boat met the pirate, then it will lose all the food pellets it carries with it. So the first question, like A and B, are a relaxed version of question C. And they're relaxed, and if the heuristic is admissible here, it will definitely be an underestimate of the previous problem. So this will also be admissible. And H2 is consistent. We can also apply this method of thinking. This is also usually how we come up with the heuristic. So So the previous problem is also still a relaxed version of this one. And so it's also H2 is also consistent. And for C, H3 is still guaranteed to return an optimal solution when used in a star search for the new problem. This is actually false. Why it is false? In one special case of H3 is on all the path, like on all the optimal solution, the heuristic is really, really big. But on other not optimal solutions, the heuristic is just 0. So so we change this game. In the new game, it may expand other like non-optimal state previously, but now since they're 0, then the cost between like they may not be consistent. And also given different kinds of solutions, we can like which are not consistent nor admissible, we may also come up like in the new search, they may also not be admissible. So this H3 should not be a correct answer. For last question, we run UCS to find optimal solution. And we have a limited memory at most X states to be stored on the frontier. B be the branching factor and C be the cost. So we should determine the upper bound on C on the cost of the optimal solution. So first we need to know is if the cost between states are only 1, then UCS will behave just as BFS. Then the cost for UCS will be the depth of the trees of the search depth of BFS. Okay, so we know from the lecture, BFS, the memory for BFS will be OB to the power of D. B is the branching factor. And D is actual depth. And then this one should be allowed only at most X states. So the space, so the memory should be less than X. If we take log on both sides, we just get log B X should be large than D. Then we've said it before, for the UCS whose costs are all 1, then it will just behave as a BFS, and the depth is just the cost of UCS. So D equal to C. So actual C should be less than or equal to, oh, this one should be equal. So C should be less than or equal to log BX.